Okay, please.
Good morning, everyone. I would like to start with introducing myself. My name is İlhami Selvi. I am from Turkey, from Middle East Technical University. I am an undergraduate student. I haven't graduated yet, and I am studying second year currently, studying electrical and electronics engineering at Middle East Technical University. And my supervisor is Muhammed UCAR from Sakarya University. He is an associated professor at Sakarya University. Okay. Anyway, this is my first paper and first presentation for a conference. So sorry in advance if I make any big mistakes. And I would like to start with the layout of our paper. And before that, I would like to mention what my paper is. It is rule-based detection of death risk in heart failure patients. And let me start with the layouts. First of all, I will talk about some background and objectives. And later that, I will talk about our data sets and how we worked on our data sets, and I will show you some statistics. Then I will mention how we manipulated our data set to make it applicable for our study, which includes methods such as feature selection, systematic sampling, and feature sorting. And after all of these, we got our data sets ready. I'm going to planning to finish my presentation with results and discussion section. Okay, let me start. First of all, I would like to define what heart failure is. As much of us know, it is not a disease actually. It is a disorder of heart, such that the heart cannot pump enough blood to the body, which is very likely to cause serious diseases such as cardiovascular diseases. And according to World Health Organization statistics, over 18 million death cases occur every year due to the cardiovascular diseases. This number is way much higher than what cancer does to people. As you can see on the graph right side, the cardiovascular disease shares the biggest part of the cake. Moreover, late diagnosis of heart failure could lead to really severe, really important and risky heart surgeries, open heart surgeries, or even worse, the heart transplant could the worst thing that a patient could face. Therefore, early and fast diagnosis of heart failure is crucially important for us. To provide this fast and early diagnosis, artificial intelligence methods would be extremely useful in our opinion, and it will be very convenient if the created artificial intelligence model would work accurately and fast. So in order to achieve this, we designed a decision tree model that predicts the condition of the heart failure patient in the near future. It takes the information provided by our data set and then gives 1 and zeros as an output. It represents 1 and zeros. 1 represents the death risk of our patient and 0 represents vice versa. First, let me give you information about our data set. Our data set consisted of 299 patients' information. Some of them are demographic information, such as age, gender, does the patient smoke or not. And most of our data based on clinical test values, such as platelet value, serum creatinine, serum sodium, and ejection fraction, and so on and so forth. We needed to make some regulations before we start on our decision tree model. First of all, we wanted to sort features with respect to their relevance. To obtain this, ETA scores of features are calculated with a formula, and we sorted them from the highest ETA to the lowest. Highest ETA score means that it is the most relevant feature with the condition of the patient. So as you can see on the table on the right side of the screen, but the most relevant feature turned out to be time, and the others were serum creatinine, ejection fraction, and age. The others were less significant compared to the first four features. This part was necessary, in our opinion, because we had to decrease numbers of features to provide a faster diagnosis in a less amount of time. And after that, we had to arrange our data set. We had to equalize our male and female patients in order to provide a more homogenic data set, and this could lead to our model to work more homogeneously. Then we used the systematic sampling method to equalize this. So it was more like a random choose. We did not affect the choice of male and female patients. Then after this implementation, we had 96 male patients and 96 female patients. In total, we had 192 samples. So first we had 299, but we had to decrease it to equilibrate our data set. Then after all of this, after we reduced after we equalized our number of patients and we sorted our features, we started to work on our decision tree rule-based model. And to work on that, first we divided our data into two. 50% of our data was to work on training, and the other was to work on the test data. And first of all, we run our model on several occasions. First of all, we started with 12 features, and then we worked on just one feature, then two features. After we worked on three features. So as you can see on the graph on the right side of our screen, we reached a local maximum value at three features. First of all, we did not do this only once because we thought that this would be a coincidence. So we tried it on multiple times, and we mostly got the peak values on three features, on accuracy, kappa score, and sensitivity performance values. So after this stage, we thought that working on the three features would still be convenient and we will still reach high accuracy. And after this step, we continued our study with three data sets. And as you can see on the screen, we have our results data. The blue columns represent the training data, which is more easier to reach higher values for an artificial intelligence model. And the gray columns represent our test scores, which is our main scope on this work, because the test scores are consisted of samples such that the artificial intelligence model have never seen before. So this was more important for us. And as you can see, both values are highly close to each other. Both training and test values are really close for both sensitivity and specificity, and other accuracy, F-score, kappa, and area under curve values are even closer. So these values are not static, of course. This could change each time you create an artificial intelligence model. But the other thing that I have just mentioned, the peak at three feature thing, was not coincident. And conclusively, I can say that knowing only time, serum creatinine and ejection fraction, which were the first three features of our patients, you can detect the death risk on heart failure patients with high accuracy with this rule-based model. Once the other clinical steps, such as platelets that I mentioned before, creatine and phosphokinase, serum sodium, or serum creatine are avoided, a procedure would continue even faster, and this model could be used as this model could be used as a decision support system that can help cardiologists to control symptoms of heart failure patients. This is all I would like to share for now. Thank you for your attention and thank you for listening.
Thank you for your presentation. Have you any question? Okay. I have a question. Where did you get that data set? How did you get it?
Yeah, we didn't collect this data set by going to hospital and asking for doctors to enable us, but we found our data set on an online machine learning repository, which is a pretty widely used data set website, I guess. So it was easy to retrieve the data set. This was the easiest part of our study, probably.
Okay. Thank you.
You're welcome.
Again. The third presentation is titled Propagation of Gaussian beam in the atmospheric turbulence. Presenter is Gamze Nur seçilmiş. Okay, please presentation Gamze Nur.
Good morning, everyone. It's a pleasure to welcome Professor Dr. Mehmet Cünkaş and the other audience in this session. My name is Gamze Nur seçilmiş. I'm a graduate